Hello, this video is going to be part 2 of my series on essential theorems for harmonic astrology. And in this video, I'm mainly just going to go over some basic definitions. It's not going to be all that long. So let's see if I can go ahead and share my screen. This will take just a minute, and I've got to get rid of some panels so that I can see what I'm doing. So just bear with me. We're almost there. Okay, and we're ready. So, essential theorems for harmonic astrology, part 2, quantitative definitions. In this presentation, the entire presentation, not just this video, we will prove theorems and results only for natural number or counting number and other positive rational number harmonics, and we will make extensive use of modular arithmetic. This is similar to what many people know as clock arithmetic, where once we reach 12, we literally start the clock over with 1 as the next hour. Thus, for example, instead of saying 16 o'clock, we either subtract 12 or look at the remainder after division by 12. And in each case, we get 4 o'clock instead of 16 o'clock. Also, in mathematics, we always start our clock with 0 instead of 12, since 12 divided by 12 yields a remainder of 0. However, we don't restrict ourselves to doing clock arithmetic just modulo 12, to use the mathematical term for clock arithmetic. And most of the time, we will focus on results modulo 360 degrees, since that is the common way to divide up a circle in both astrology and mathematics. Hence, we will write things like 240 degrees modulo 360 degrees just gives us back 240 degrees. However, 420 degrees modulo 360 degrees is equal to 60 degrees. If you subtract 360 degrees from 420 degrees, you'll get back 60 degrees. And that's the same result you get if you divide 420 degrees by 360 degrees and look to see what your remainder is. And 720 degrees modulo 360 degrees is equal to 0 degrees, since 360 degrees divides evenly into 720 degrees with a remainder of 0. Okay, harmonics in astrology can also be defined for negative numbers and for irrational numbers. And many of our theorems will also apply to these other real numbers, but they aren't generally needed. Negative numbers can be ignored for now for the same reason that we can always say 9 o'clock instead of negative 3 o'clock when denoting time. And irrational numbers, while theoretically important, don't obey many of the rules that apply to other harmonics. And in practice, they can always be closely approximated with any desired degree of accuracy by a rational number. With that said, in order to keep things simple, for now, in the future, we might go into these irrational things more deeply, but for now, we'll focus primarily on positive rational numbers and their subsets. Now let's make a few definitions. Definition 1, a counting or natural number is any one of the numbers 1, 2, 3, 4, etc. that we count with. The set of counting numbers is symbolized by a block letter N, and we also call these numbers natural numbers because we think of things in nature as occurring in these units. For example, we count 1 rock, 2 rocks, and so on. We don't count 1 rock, look at the next one and say, well, this one's pretty big. That's like 10 2/3 rocks. And then the next one's really tiny, so that's maybe just half a rock. No, that's not the way we count it. Things in nature count as 1 rock, 2 rocks, and so on, or 1 tree, 2 trees, 3 trees, and so on, regardless of the size. Okay, definition 2. A whole number is any one of the numbers 0, 1, 2, 3, 4, and so on. The set of whole numbers is sometimes symbolized by a block letter W. So the only difference between The natural numbers and the whole numbers is the inclusion of zero when we're talking about whole numbers. Definition 3. An integer is any one of the numbers 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on. And the set of integers is symbolized by a block letter Z, and the set of positive integers is symbolized by Z plus. Now, if you think of the number line, the points on the number line correspond to what we call real numbers. And they're called real numbers because we think of the real numbers as the numbers that apply to the real world. And then on our number line, the points or numbers that we usually mark off for our scale are the integers. 0, 1, 2, 3, 4 in the positive direction, and then -1, -2, -3, -4, and so on in the negative direction. So if you are familiar with the number line and the numbers usually used for the scale on that number line, that's an easy way to remember what the integers are. Now let's take a look at definition 4, a rational number. And let me make a quick confession here. When I was in elementary school and first learned what rational and irrational numbers are, I had no problem with the definition, but to me, the word rational meant sane, and irrational meant insane. And for years, I could never understand why some numbers were called sane and other numbers were called insane. Well, I eventually figured it out. In mathematics, the word rational always refers to some kind of ratio, and hence, a rational number is a number that can be written as a ratio of two integers, such as 1/2 or 2/3, or -6/5. A rational number can also be defined as a real number whose decimal expansion is either terminating, such as 0.125, or is non-terminating and repeating, such as 5.232323, and so on, where that 23 repeats forever. The set of rational numbers is symbolized by a block letter Q, and the set of positive rational numbers is symbolized by Q plus. Okay, definition 5. The irrational numbers are real numbers with decimal expansions that are both non-repeating and non-terminating, such as square root of 2 or pi. The set of these numbers is sometimes symbolized by a block letter H, with the positive irrational numbers represented by H plus. Definition 6. The real numbers are the numbers that correspond to points on the number line. They also consist of the rational numbers combined with the irrational numbers, and they are symbolized by a block letter R. Similarly, the positive real numbers are those real numbers that are greater than 0, and they can be symbolized by R plus. Okay, definition 7. The least common multiple, or LCM, of two rational numbers is the smallest quantity that is a counting number multiple of both. In particular, if A, B, C, and D are natural numbers, then the least common multiple of AB over CD is equal to the least common multiple of AD over BD, comma, BC over BD, which is equal to the least common multiple of AD, comma, BC all over BD. Got it? Well, let me break that down for you. Most of the time when we're finding the least common multiple of two numbers, we're just doing it with natural or counting numbers, such as when we say that the least common multiple of 4 and 6 is 12. But in our work with harmonics, we're going to sometimes have to find the least common multiple of fractions. And the way we do it is we rewrite those fractions with a common denominator, and then we find the least common multiple of the numerators of those fractions, and we put the common denominator down below. Okay, definition 8. If a and b are real numbers, then a is a divisor of b if and only if there exists an integer k such that k times a equal b. Note that a divisor is defined in terms of multiplication rather than the division, say, b over a equal k. This is so that we can get around 0 divided by 0 being undefined and still claim that 0 is a divisor of 0. Now, that's a technical point, and it's really not going to arise later on, so don't worry about it. Definition 9. The greatest common divisor, or GCD, of two rational numbers is the largest quantity that yields a counting number when divided into each of the rational numbers. In particular, if a, b, c, and d are natural numbers, then the greatest common divisor of the fractions a over b and c over d is equal to the greatest common divisor of ad over bd, comma, bc over bd. You just write those fractions with a common denominator, and then that is equal to the greatest common divisor of the two numerators divided by that common denominator. Okay, we have just a few more definitions to go. So let's see, definition 10. If r is a positive rational number, then we will call the angle 360 degrees divided by r the root r angle. And we will call theta sub r equal to 360 degrees over r modulo 360 degrees, the root r harmonic angle. We'll additionally call r the corresponding harmonic. Now, for most of what we do, the root r angle and the root r harmonic angle are going to be the same, because most of the time we're going to be dividing 360 degrees by natural or counting numbers. Okay? But theoretically, and sometimes, we might divide 360 degrees by a fraction, such as 1/2, and that is going to give us back something larger than 360 degrees. In particular, 360 degrees divided by half is going to be 720 degrees. But we want our root harmonic angles to always be between 0 degrees and 360 degrees, specifically greater than or equal to 0 degrees and strictly less than 360 degrees. So 720 degrees, that would be the root 1/2 angle, but 720 degrees modulo 360 degrees, which is equal to 0 degrees, that is going to be the root 1/2 harmonic angle. I hope that clarifies things. Okay, definition 11. If theta sub r is a root r harmonic angle for some positive rational number r, then by a r harmonic angle, we mean any angle of the form k times theta sub r modulo 360 degrees, where k is a natural number. So our root harmonic angles, they are going to be our r harmonic angles are going to be natural number multiples of our root r harmonic angle, but we want to express those multiples modulo 360 degrees. We're not going to go over 360 degrees. Okay, notice that for a natural number n and root n harmonic angle, theta sub n equal to 360 degrees over n, the number of distinct n harmonic angles is equal to n. And they are theta sub n, comma 2 times theta sub n, comma 3 times theta sub n, all the way up until we get to n times theta sub n, modulo 360 degrees, which will be equal to 0 degrees. Over here, if you take 360 degrees over n, which is theta sub n, multiply that by n, the n's will cancel out, leaving you with 360 degrees. And 360 degrees modulo 360 degrees is equal to 0 degrees. So we're not going to have an infinite number of r harmonic angles. We keep multiplying that root our harmonic angle by natural or counting numbers until we get to 0 degrees, and then that's going to be when the clock starts over. Okay, definition 12. If r is a positive rational number and theta sub r is equal to 360 degrees over r modulo 360 degrees, the root r harmonic angle, then we'll denote the set of all r harmonic angles by h sub r equal to k times theta sub r modulo 360 degrees, where k is a natural number. And even though we have an infinite number of natural numbers, this set's not going to be infinite. We're eventually going to get to 0 degrees, and then we start repeating the values again. Okay. Furthermore, we'll consider H sub r to be an ordered set, where the order of the elements corresponds to increasing values of k. And we'll call this the natural order for H sub r. So let me show you a few examples on the next slide. H sub 2, well, if you divide 360 degrees by 2, you get 180 degrees. So this is going to be the second or 2 harmonic. This will be the root second harmonic angle. Okay? And then you add 180 degrees to this, or you do 2 times 180 degrees. Express the result modulo 360 degrees, and you get back 0 degrees. Now, if you continue on, the next one, modulo 360 degrees, is 180 degrees, but that's already in our set, so we don't repeat the values. We've got all the values right here. H sub 3, the root third harmonic angle is going to be 360 degrees divided by 3, which is 120. And you look at 2 times that, you get 240 degrees. You multiply this by 3, which is the same as adding another 120 degrees to this guy. You get 360 degrees, which is equal to 0 degrees when you express the result modulo 360 degrees. And we put everything down in this order, starting with the root harmonic angle and ending with 0 degrees. So for H sub 4, our set of harmonic angles, our set of 4 or fourth harmonic angles is 9 degrees, 180 degrees, 270 degrees, and then 0 degrees. For H sub 5, our ordered set of fifth harmonic angles is going to be 72 degrees, 144 degrees, 216 degrees, 288 degrees. Add another 72 degrees to this, we get back modulo 360 degrees to just 0 degrees. Okay, so these are some basic definitions, and if ever you need to refer back to them, you can just go back to this particular slideshow, and I think that's going to be it for now. So let me stop sharing my screen. And I'm back. So that is going to be the end of this presentation, part 2. And I hope you enjoy me. I hope you join me for some more of these little presentations. If you're interested in the mathematics of harmonic astrology, it's kind of a specialized topic. Not everyone is going to be interested in it or suited for it, but if you are, then listening to these short little lectures that may help you understand the written material a little bit better. So I hope you join me again. And for now, I'll just say so long and be well.